Alright, so in the ad hoc networks, we will talk about what are the key characteristics of the ad hoc networks, where it is used, what are the issues, then we compare the cellular versus ad hoc networks, and then the key areas of research actually in ad hoc are in routing. So after a brief introduction to why the routing is an issue, we talk about 3 of the well-known routing algorithms. Actually, again, just like TCP, there are hundreds of algorithms that have been proposed for ad hoc networks, but we talk about those 3 that have been actually selected for implementation by IETF. And so these are more real than many of the other proposals which are only theoretical. So these 3 are DSR, AODV, and OLSR as shown on the slide. So we'll talk about those 3. So first of all, what is an ad hoc network? Ad hoc network, we already know, is one in which there is no base station. So you can have a cell phone talk to another cell phone, or a computer talk to another computer, or a computer talk to many computers. So if you make a network out of all these different computers which are talking to each other, it makes a network. And not only a network, each of the computers is actually acting as also as a router. So when somebody from one end of the network wants to talk to somebody else at the other end of the network, they may not have a direct wireless link. And so they will go through these different computers and different nodes. And so obviously everybody has to be a router and has to know about the routing and connectivity, and so it's kind of tough problem. And the problem becomes tougher because each of these intermediate nodes might be moving, so the topology can keep changing. So unlike a fixed network where we can do routing much easier, here the routing problem is much more dynamic. And then third thing is, because all of these might be using the same frequency, so there is a question of who can speak when. So there is a question of spectrum reuse because they're using the same frequency. So when A receives a message from B, then it has to translate it. It has to transmit it to C. All of this is being done at the same frequency. So that is one problem. The usual problem of having obstacles in the wireless path is there. And the energy conservation issue is there too, because all of these might be running on batteries. Then self-organization, and that is the issue of basically not the whole thing has to organize itself and dynamically change as the nodes get in and out of the network. The remaining nodes have to form a network which is fully connected somehow. And so there is an addressing issue first of all, then there's a routing issue, there's a clustering issue. Clustering means basically who can come and join this group, and then the location and the power control. And some of these are actually the usual wireless issues, such as power control. In case of location, basically we need to find out who is where so that we can go through the route which is much more logical as opposed to just whoever can hear whoever. Alright, the fourth issue is energy conservation, which we already talked about. Energy conservation is basically the issue of battery life. Scalability. Sometimes these ad hoc networks can be very large. So where are the ad hoc networks used? Actually, one of the most common usage is in the military. In the military, if you have lots of soldiers, they could be talking to a cell tower, but if they talk to a cell tower, I'm sure that the enemy will first attack the cell tower, and therefore oftentimes they use radios that do not use any centralized facility, and so the ad hoc networks are much more suited for those environments, and there could be thousands of those nodes. And so the scalability is an issue. Security is an issue just like any other wireless. And then bandwidth constraint. So the congestion is a norm, basically because there are so many people trying to use the same link and same nodes. The congestion is they're generally highly overloaded. So all of this actually is very well described in RFC 2501, And this is just a summary of that RFC as to what is the issue of. By the way, there is a group in IETF called MANET actually, MANET, Mobile Ad Hoc Networks. And so MANET actually has produced many RFCs, and 2501 is one of the first ones. And the remaining three RFCs that the three routing protocols that we'll talk about are also results of MANET. All right, applications. I think I was a little bit ahead on the applications before, but here is a whole set of applications. So one set is in emergency and disaster situation. So if there is a problem in an area, then we quickly want to talk to each other. And the emergency crew, generally they cannot be, they may not have the access to and they not have access to a cell tower, because cell tower either doesn't exist in this area or it has already been destroyed. And so whenever there is a disaster or emergency, the ad hoc networks have to work. Wearable computing is another new application coming up. As we are going to have many computers on our body, we are not going to have a cell tower there. And so they have to be able to talk to each other in some ways. And so that actually, when we talked about the personal area network span, we did talk about that they have routing, and then they're routing nodes and full featured nodes and so on and so forth. Those are very similar to this variable computing issue, computing issue, where we use ad hoc networks. Battlefields we talked about today, unmanned, ground, airborne, underwater vehicles. Any of the most of the military communication generally does not use any centralized point of failure or centralized point of communication, and so they will use ad hoc networks. Hybrid. Sometimes what happens is you have a cellular network, but cellular networks may not be able to reach certain areas of the city. Say for example, in a particular street, then you might go there multi-hop. Multi-hop means that you could go to some relay station, and then from the relay station you could go to people on that street. So that's a hybrid because it has a cellular as well as the ad hoc networks. The next one is the mesh network, and the mesh network actually is a generalization of ad hoc networks, and generally the word mesh is actually, we probably will have a whole lecture on mesh if time permits. But generally the mesh networks are used when instead of a cellular network, we may want to have whole community of people or houses which are connected together, and so each house acts as a router for other people, and so that is basically mesh is a special type of ad hoc. And similarly, sensor networks is a special type of ad hoc. And we are going to have, the next lecture actually is going to be on sensor networks, so we are going to talk in more detail about sensor networks. But in this lecture, I thought I will just give one slide overview of what is a sensor network, and then we will have the whole lecture next week. All right, so sensor networks, basically sensors, as we know, are devices that can sense either the temperature, humidity, or anything, like carbon monoxide or anything else they can sense. Now the issue is that all that information that they have just sensed has to be transmitted to some central place, and so we need a network. And this network has a requirement that we just talked about actually for ad hoc networks, but even more constrained in terms of energy, because most of these little sensors have batteries which have to last for years. And so in a sensor network, generally we say, we might have a sensor which is, let's say, moisture sensor in a field, in a corn field, or in a agricultural field. And so we have to know where the water is not reaching or where the water is too much. So all those sensors will talk to each other and somehow get the information from the sensor field to the sink. Sink is where all the information is being collected. So that's the node where all the information is being collected. and from there it will go on the internet to some place where it is being managed. So the task manager actually is maybe far away and connected to this thing by the internet, and so the sensor field is basically a whole bunch of sensors, which all of them have some short distance networking capability, but these are very low cost, very low power devices. And so the key issue is that generally sensor networks are very large scale. You could have 10,000 sensors very easily, and they have very limited power consumption. They have high fault tolerance because basically the sensors and devices can become inoperative quite a bit. So we put so many sensors generally that if one or two, if they failed, it doesn't make any difference, or if certain percentage failed, it doesn't make any difference. And data fusion is basically the idea of combining this information. So if you get, let's say, from 4 sensors which are next to each other, the temperature is 25 degrees, or the humidity is whatever number, 200 or whatever number is. So the question is that you don't want, you can either send probably 4 messages, or you could combine those and people will know that in this region the temperature is 25 degrees. So that is called data fusion, is combining similar data, and so somehow we have to be sensitive to the location and the information, and that has to be combined. So that's another field. And then the traffic, basically it's very low throughput traffic. You get a temperature change maybe once in an hour. That is only few bits per hour. And once you get that, it is very delay sensitive, because if something happens, let's say your carbon monoxide sensor, you may want to know that within a few seconds or few minutes before something serious happens. And you can imagine that there are even more sensors which can be very critical, such as in the military and deployments. So anyway, so the whole, in the last several years, there has been quite a bit of research funded by NSF on sensor networks, and that has been a hot topic. So we will have a whole lecture on sensor networks next time, and in fact at the university we have probably several courses on sensor networks. So so we will talk more, but today at least we realize that the sensor networks are a type of ad hoc networks. I have listed here the top 10 issues. First issue is that of medium access. As you can see, that since we don't have a centralized access, there are several differences from what we talked about in WiMAX, because first of all, it is distributed access. Anybody can speak whenever they want. There is no time synchronization because there is no central point to which they can synchronize to. And the antennas could be directional, in this case, because we know where the other nodes are and we could be listening more in that direction. So the medium access actually generally for ad hoc networks is the one that we have kind of discouraged in the past, and that is CSMA, carrier sense multiple access, simply because the other one, which is more coordinated centralized access, is not possible in ad hoc networks. So most of the ad hoc networks generally use some variation of CSMA. The second issue then is routing. Now routing has the problem that we may not need. Suppose I collect all the routing information, and I continuously collect all the routing information. It may not be of any use because we are going to use it only once in a few bits transmission in an hour. So by the time I need it, either the information is either too old, or I have to just collect too much information just to transmit very few bits. So generally the choice is whether to do the routing when we really need it, or to do the routing before we need it. So if we do it when we need it, then the delay in finding the route actually is the route acquisition delay, which is an issue. And then quick reconfiguration is the issue, that if somebody moves out, which people do because these are all mobile nodes, we have to be able to take care of that very fast and loop free. And it's just like any other routing issue. We don't want to be going around in a loop, otherwise the message will never get out. And so so we really need a bigger picture of the whole network to ensure that there are no loops. Then there is a lot of research in multicasting, and multicasting is actually very common in ad hoc networks, because whenever we want to send send some key piece of information to all the soldiers or emergency situation, we really need to multicast that. And so while the multicasting comes very naturally and very cheap in a centralized network like WiMAX, it is very resource consuming in the case of ad hoc networks. Transport layer. So all the issues, the wireless TCP are still here. In addition, basically the frequent path breaks. The issue is that people are moving in and out, so the packets may really get out of order and get lost, and all those issues are there. Quality of service. Now, how do you really do any video or anything that requires guarantees in this situation where we really have so much dynamics? It's much more difficult than, quality of service has not been solved even in the wired networks, let alone in wireless, and then let alone in ad hoc networks, which are kind of difficult case of wireless networks. Self-organization. We talked about that. Basically, the issue is that to find out who your neighbors are, and then who their neighbors are, and so on. So really the whole neighborhood discovery. And then if you have discovered something and something changes, then again trying to find out, trying to propagate that information that the link has failed. Seventh issue is security. Denial of service. Somebody can jam the whole area. Energy depletion, batteries running out on several nodes. So, and then comes the issue of energy management. How much power will be using? How much, and the battery has to be carefully monitored. But also the question is, if transmission power is one and the processing power is another, because processors also take battery. So when we do routing and all that, we have to be worrying about as to how much energy we are using for routing, both radio transmission as well as for routing computation. Addressing and service discovery. So basically, do we need global addressing, and how do we find out different nodes? So there have been some proposals on different types of addressing for ad hoc networks. And then the pricing scheme, incentives are relaying. So one of the actually failures of ad hoc networks has been that we have not been able to use it in the real world other than military world. So for example, there was a dream a few years ago that one could have a service where one home could subscribe, for example, to DSL service, and then the whole neighborhood could basically share it with another ad hoc network. Or one could subscribe to a wireless link, and then the whole neighborhood could really get it from them by relaying by different houses. But the issue is, why would somebody want to relay the traffic to somebody else? And what is the economic model for it? How do people make money who are relaying? How do they get reimbursed for all their effort and the subscription that they have to do? Those problems actually have not been solved. And so really and that's actually has affected what we call the mesh networks, is that they have not really materialized in the real society as much as they have basically done in military and emergency situation where economics is not really an issue. So anyway, but there are some papers on pricing schemes to make it good for people to be able to use the mesh networks. So these are the 10 areas where there are lots of papers in each of these areas. We will actually concentrate just on routing part in this lecture today. In fact, there are whole set of books on just on ad hoc networks alone, so one could have a whole course on ad hoc networks. This being the first course in wireless networking, I think this is appropriate that we give sufficient exposure in case if you want to do research in ad hoc networks or you want to get into more detail, then you can get into these other topics. And this is just a summary of cellular networks versus ad hoc networks. Most of it has already been said, but I will just repeat it. First is, in the cellular networks, we have a central base station. In ad hoc networks, there is no centralized stuff. Most of the cellular networks are single hop. You go from the mobile stations to the base station, and so that is one hop, or from base station to the mobile station. In the case of ad hoc networks, when you go from A to B, you might go through several wireless hops. So this is multi-hop network. The routing in the cellular network is centralized. In ad hoc networks, is distributed. In cellular networks, they are really prone to failure because the base station goes down, the whole network goes down. And ad hoc networks, if one node goes down, if one node is shut down or one node is destroyed, the network still really stays intact. So it's very resilient to failures. Seamless connectivity. Generally, the connectivity remains the same as long as you are inside the cell. But in the ad hoc networks, because people are moving, the links are frequently breaking, and the routing information changes very fast. High cost and long deployment times. Now, because you need to set up a tower, you need to set up a antenna and all that on the top of the tower. It takes quite a bit of time, several months to set up a cellular network. But ad hoc network can be set up in few minutes or few hours. And so that's why they are used in emergency situations, in military situations, because they are really in a hurry to set it up. Commercial sector has generally preferred cellular networks, and the military and the emergency and disasters departments have selected the ad hoc networks, have preferred the ad hoc networks. The cellular networks are simple. The mobile nodes are very simple, and the base stations have all the complexity because there is only one of them. Whereas in ad hoc networks, all the nodes are equally complex. All of the nodes generally have to do the transport and the networking and everything else talked about. So the mobile stations are rather complex with ad hoc networks. No forwarding fairness issue. So one of the issues in ad hoc networks is that how much energy and time and resources you devote to forwarding other people's traffic versus your own traffic. When you have the load which is close to 100%, should you just be having 90% of it for yourself, or should you have 50% of it for yourself, or should you have 10% of it for yourself, because there are 9 other people sharing the same thing through your network, to your node. So there is a whole issue of fairness which doesn't exist in case of cellular networks. I mean, cellular networks, the fairness is rather simple, where you want to make sure everybody who has a similar traffic gets the same kind of throughput, which is much more easier than worrying about whether we transmit or forward. Then the issue of time sync, because everybody can synchronize to the base station, we can very easily use TDMA, time division multiple access. Remember, in time division multiple access, if 2 different nodes basically need to transmit, they have to take their time slot, and they have to know exactly where the time slot begins and where the time slot ends, so that they don't run over into each other's time. So TDMA requires time synchronization, which is possible in a cellular network or easy in a cellular network. In a ad hoc networks is very difficult, and therefore we don't generally use TDMA. We use CSMA, carrier sense multiple access. And then static frequency reuse. Now here in the cellular world, we design in cells, and then we assign frequencies to each cell and each sector, and we keep that for years to come because we don't change. Whereas here in the ad hoc networks, the nodes are going in and out every few minutes, and therefore the frequency reuse as to what frequency can be used where is very tricky because it changes so fast. Alright, so this is a repeat or summary of what we have said so far. The main thing is that in the real world they have not succeeded is because of the cost and because of also the issue of fairness as to, economics. Economics is cost part, and economics comes in two ways. One is that the nodes themselves are more expensive than a base station based network, and second is the issue of how do you get paid for the forwarding traffic, and there are no satisfactory solutions for those. All right, so first thing is the media access control. We talked about 10 issues, and so media access control is the first issue. And the problem we already talked about is that for media access we cannot use centralized versions of like WiMAX, so we have to use CSMA. And then there is a problem of hidden node. Hidden node means that B, as shown on the left side of the picture, can actually hear A and C, but A and C cannot hear each other. So they might transmit at the same time to B, and they might collide at B. So the B cannot really hear either of them, but both of them think that the media is really totally clear. So basically, carrier sense doesn't really, completely work in this situation, because you can sense the carrier and C can sense, for example, the carrier and see that the network is idle, but it cannot really hear the transmission from A, and so network may not be idle. So one has to use something more than carrier sense. And does anybody remember what did we use in 11 along with CSMA to ensure that we get the medium when we need it? There are 2 extra packets that we send. Okay, so diffs and sifs had to do with the issue of how long to wait before somebody else. So that is one good thing, yeah. But the thing is, diff and sif will not solve the hidden node problem. What was the solution for the hidden node problem in Wi-Fi? Okay, so there are 2 packets that you have to send before you send your data packet. Well, those 2 packets are called RTS and CTS. Remember, request to transmit and clear to transmit. So if RTS goes through, then B will know that, okay, now I'm going to get it from A, and then it will reject C's request if it also came around the same time, so only one of them will transmit to B. So hidden node problem was solved by RTS CTS combination. So you really sent 4 packets instead of 1 packet. Basically, first you do request to transmit, then you got the clear to transmit, then you send the data, and then you got the data acknowledgement. So that is the solution to a hidden node problem. The other issue is that of the exposed node, and that is the issue where some other nodes, they cannot talk because one node is talking. So if when A talks to B, C cannot talk to D, because if C talks to D, it will be interfered by the transmission from A. And so this is called exposed node, that there are nodes in the vicinity of the network that cannot really get their own service. And so for that, basically we can use directional antennas, so that the energy from A going to B doesn't really go in anywhere close to C or D. And it is, and so then there are directional antennas and there are steerable antennas. Steerable antennas means that you could have a whole set of antenna array, whereby changing the phase of the signals to each of these arrays, each of the element in the array, you could change the direction of the antenna to any direction you want. So you could very dynamically change the, talk to first, for example, when you're talking to A, your antenna is basically pointed towards A, and then dynamically you can change it towards C, D, E, F, G, whatever you want to do by just changing the phase. So that is called steerable antenna. And so the media access method, which is generally used in ad hoc networks, is what we call, and one of the proposals actually is MACA, with multiple access with collision avoidance. And there are many proposals for access, for media access. Like we said in our slide, there are 10 issues in ad hoc networks, and there are many papers on each of those 10 topics. So similarly, there are many papers on media access control, and MACA is one of them. And MACA basically uses this RTS, CTS with binary backoff, as we talked about in 802.11.